So for this lesson here, we're going to talk about the different types of symmetries. So the first one that's usually talked about is basic line symmetry. Line symmetry is a line that divides a figure into two mirror images, and the figure is mapped onto itself by a reflection in this line. So you can think mirror image here. So let's take a look at the definition of a line symmetry. A line symmetry is a set of points, or if and only if there is a line L, such that the reflection through L of each point in the set is also a point in the set. This is also referred to as reflectional symmetry. So, big confusing definition. It's really not as confusing as it seems. So if we look at this line L here, this is one of the lines of reflection for this hexagon, meaning if we folded this hexagon over this line, it would be a mirror image. There are a lot more lines of symmetry, obviously, in a hexagon. We can fold along this line. We can fold along this line here. Now, we have to make sure we realize that certain figures have line symmetry and certain figures don't have line symmetry. We could also add in a couple more lines of symmetry in here. We have one here, we have one here, and then we also have one line of symmetry here. So let's take a look at some examples of figures that have lines of symmetry and don't have lines of symmetry. A scalene triangle, meaning a triangle with three unequal sides and three unequal angles. There are no lines of symmetry in this figure. That means that we cannot draw any lines to fold over to get the exact same thing. What about an isosceles triangle? An isosceles triangle has a line of symmetry because an isosceles triangle has two congruent sides, which allows us to draw one vertical line that it can fold over. A rectangle has two lines of symmetry, one going vertically and one going horizontally. And then another example would be a square. A square has diagonal lines of symmetry as well as vertical and horizontal. So let's look at things that, we should be aware of with non-symmetrical figures. Now, a rectangle does have the lines of symmetry as we mentioned here, but the diagonal is not a line of symmetry because if you look here, they don't fold on top of each other if you were to do that. It appears like it does, but you have to make sure you take notice to the fact of it would really end up here if we tried to do that. And the same goes for a parallelogram. Now, a parallelogram, we think, oh, this must have lines of symmetry. No, if you were to fold up, as you can see here, there are none. So beware of figures that look like they might have lines of symmetry, but do not actually have that. So now let's go and move on to a different type of symmetry. Actually, we're going to look at a couple more. So in regular polygons where all sides are congruent and all angles are congruent, that's what a regular polygon is. The number of lines of symmetry equals the number of sides. So let's take a look at a regular polygon. This is not a regular polygon. This is just some scalene triangle. This is an isosceles triangle. So it only has one line of symmetry. It's still not a regular polygon. And we just established that a parallelogram does not have line symmetry. But how about a square? A square is a regular polygon. So let's take a look. Based off of this piece of information here about regular polygons having the same lines of symmetry as the amount of sides they have, here's 1, 2, 3, 4 lines of symmetry. So that coincides with that. Here's a rectangle. A rectangle is not a regular polygon. This only has 2 lines of symmetry, but a rectangle has 4 sides. So again, any regular polygon has the same lines of symmetry as the amount of sides it has. Let's take a look at this octagon. Here is 1, 2, 3, 4, 5, 6, 7, and then our 8th. So there's 8 sides. There are 8 lines of symmetry. So now let's take a look at a different type of symmetry called point symmetry. A figure has point symmetry if it is built around a point called the center. such that for every point on the figure, there is another point directly opposite and at the same distance from the center. A figure has point symmetry when it looks the same when upside down or rotated 180 degrees as it does right side up. So let's take a look here. If we took this point here and went across, it would be the exact same distance to the other side. Same goes for here to here. That is what we call point symmetry. We're looking at points. Don't get this confused with line symmetry. So we're going to talk about rotational symmetry as well. So keep this piece of information here in mind. So now let's look at some examples of point symmetry. So a parallelogram did not have line symmetry. Remember, if we tried to draw any lines that would fold up and give the exact same thing, it would not work. But this does have point symmetry because if we are looking at this point here and we go to the center, there's another point the same distance away. Same goes for a point here. Same distance away. Same goes for a point here. Same distance away. So that is the difference between line symmetry and point symmetry. Rectangles also have point symmetry. And again, we mark our center. From this point to the center, and then from the center to the opposite side at the same point is the same distance. We also have that here. We could add in another one here. We could also add in the same thing here. Now, let's look at an isosceles trapezoid. Here's the center of an isosceles trapezoid. This does not have point symmetry because if you go from here to the point on the opposite side, these are not the same distance. And same goes for here, and same goes for here. An isosceles trapezoid does have line symmetry, though. It has one line down the middle. So just because it has line symmetry does not necessarily mean it has point symmetry. Same goes for the equilateral triangle. This has line symmetry. There's one that goes down the center because these two sides are congruent. But if we look at point symmetry, you cannot find a point that's the same distance from the center to those points. So no point symmetry for some figures that have line symmetry. So just keep that in mind. Important fact, line symmetry does not always mean point symmetry. The next type of symmetry we're going to look at is called rotational symmetry. Now this one might be a little bit confusing. So a figure has rotational symmetry if when rotating, aka turning or spinning the figure around a center point, by less than 360, the figure appears unchanged. So let's take a look at these examples up here. So a king card. If you were to spin this 180, aka flip the card upside down, it would still look like the same card. So this does have point symmetry, or rotational symmetry, I'm sorry. This figure here, this writing of the word mom, does not have rotational symmetry because no matter how many times we try to rotate this before we get back to 360, the figure will never look the same. So we can try it 90, 180, 270, and the only time it will look the same again is when we do it 360. The Volkswagen logo, same thing. If we rotate this logo around and try to get it to look the same before we hit a full circle or 360, that will not work. So that does not have rotational symmetry, and neither does the word mom. Now, let's talk about a key thing here called the order, or N, for an angle of rotation. So a parallelogram has rotational symmetry. So let's talk about this with the concept of having an order. So if I take a parallelogram and I want to find out if it has rotational symmetry, again, so I'm trying to figure out how many times I have to rotate this to get the same image. If I were to do this twice, so 90 degrees 2 times, that's the order. The order is 2. Again, 2 rotations to get the same image. So again, if I wanted to see what the angle of rotation was, I would have to do 360 divided by 2 because that's my order. And again, my angle of rotation is 180. An equilateral triangle does also have rotational symmetry. So if I have my equilateral triangle here, that means I can do this 3 times and get the same image here. So I can rotate it once this way, once this way, and once this way to get to the amount of times I need to have the same image. I can do that 3 times. So my angle of rotation is 120 degrees because 360 divided by the order of 3, the 3 times I rotate, equals 120. And lastly, let's look at one example with the square. A square has order 4. So if I do 360 divided by 4, the amount of times I can rotate it to get the same image, my angle of rotation would be 90 degrees. So here would be 90. And if we broke it up, 90, 90, and 90. A pentagon also has rotational symmetry. So if we spin a regular polygon on its center point, and every 72 degrees it will appear unchanged, the order, sorry about that, let's get back to where we were, the order was 5. So if you spin this every 72 degrees, you will have the same figure. So 360 divided by 72 degrees, or divided by 5, sorry, our order, gives us the 72 degree angle of rotation. So 360 divided by the order gives us the angle of rotation. A little bit of a difficult concept, but if you want to spin your paper and actually look to see if it is the same image, that's totally fine. So here's some more examples of rotational symmetry and non-rotational symmetry. If I were to rotate this figure, I'd eventually be able to get the same one after some rotations. Same with the letter S. If I go 180 with the letter S, it still looks like the original picture here. This is a recyclable logo. So picture this triangle here that makes it up. You can do this 3 times and get the same figure. And then again, we've discussed the parallelogram. We can do this twice. So 1, 2 times, and we are able to get that same figure. Non-rotational symmetry, we would never be able to make this the same image before getting to 360. So if we tried to spin this a bunch of times before we got back to the start, it would never look like the same image. This example is a little tough to see here, so I'm going to disregard this one. We already have discussed the Volkswagen logo. The Volkswagen logo can't be spun at any point before 360 and look the same. And then the same goes with the isosceles trapezoid or any trapezoid in general. We cannot spin this around before we get to 360 and have it look the same. So our key pieces of information here: line symmetry, we have point symmetry, and we have rotational symmetry. So again, just to recap, line symmetry, I will use a rectangle as an example. If I put a line here, I can fold it up and get the same image on top of each other. Same goes with that. Okay, so a horizontal and vertical line work for a rectangle. Now in a rectangle, let's talk about point symmetry. So if this is the center of my rectangle, this distance to here is the same distance from here to here. Same goes for here and here. We could also draw something in here and here, as well as here to here and here to here. So that's how we do point symmetry. We go through and see if it's the same distance. Now, rotational symmetry for a rectangle, if we wanted this rectangle to look the same, we would have to rotate it twice. Okay? So the order of this would be 2, right? Because 360 divided by 2 gives us 180, which is our angle of rotation here that we have to go to make it look the same.